Shakespeare's character in Romeo and Juliet asked, "What's in a name?" We can ask, "What's in a chemical name?" Let's talk about when simple decomposition is not simple decomposition. We classify reactions in a modern way. We've been learning how to give names to types of chemical reactions. In most reactions, we know either electrons move or ions move. When electrons move, we have an oxidation-reduction reaction. So, for instance, a metal gives electrons to a nonmetal, as we've seen in some reactions, magnesium reacting with oxygen, for instance. Or we know that 2 moles of silver ions, as in silver nitrate, will react with copper wire to form 2 moles of silver metal and the blue passing light copper 2 plus, as in copper 2 nitrate. The other type of reactions we were studying were called ion swaps. When ions move, we either have an acid-base reaction or a precipitation. As an example, the silver ions in silver nitrate can react with the chloride ions in sodium chloride in solution, and the silver ions stick so tightly to the chloride ions that they clump up and fall to the bottom of the test tube as a solid. We of course call that a precipitation. An older method of classification that is still used in some textbooks can be confusing. They call it composition when we put elements together. For instance, when sodium metal reacts with chlorine gas. But we know that since that's a metal-nonmetal reaction, that must be electrons moving from the sodium to the chlorine. That's an oxidation reduction. Decomposition, they make that a real big category. And when compounds are taken apart, they call that decomposition. Single replacement, as when, for instance, the reaction we just saw, when copper metal ions take the place of silver nitrate in solution, and as you know, that's really an oxidation reduction. And then, to add to the little bit of confusion here, they have something called double replacement, and that's what we called an ion swap, acid base and precipitation. And then to give you one last category, they talk about combustion, burning things in oxygen. Sometimes they add things like chlorine instead of the oxygen, but we know that all of those combustion reactions are really oxidation reductions. Now let's talk specifically about decomposition, because we have classified everything else as either an oxidation reduction or as an ion swap. Some decomps are in fact simple. For instance, we'll get to copper sulfate in a second. Simple decompositions involve just heating something up so that the atoms, or really ions, continue to move and move faster and faster and faster until they break up, or until the molecule splits off from an ionic compound. You remember heating a hydrated salt, probably the blue copper sulfate that had the water embedded in the crystal, and it shook apart into the white copper sulfate anhydrate here, and it gave off 5 water molecules per unit. The blue hydrated crystal changed to a white powder. Well, we could have collected the water that came off of that and shown that it is in fact water. Then when we exposed the anhydrate to water, it turned back into blue crystals. That's a simple decomposition. Another type is the heating of metal carbonates. For instance, calcium carbonate, limestone, can be heated to form calcium oxide and carbon dioxide. That's a simple shaking apart. There's no oxidation number change. The calcium is +2 here and it's +2 there. And the carbon dioxide, which is really kind of trapped with the calcium oxide here, the carbon dioxide just comes off. You heat it It comes off, no energy is given off, energy is taken in. That's a simple decomposition. But some decompositions are not simple. If more than just heating the compound until it shakes apart is involved, it's not simple. For instance, we've studied potassium chlorate, and all metal chlorates will heat, if you heat them, what you get is potassium chloride and oxygen gas. And since we have oxygen gas, the element on one side, and a compound of oxygen on the other, we really understand that's not a simple decomposition. We know that we can electrolyze water and turn it into hydrogen and oxygen gases. Those are elements, of course. These are really oxidation-reduction reactions. When you do the oxidation numbers, for instance, on the chlorine and the oxygen, here you see that they change going to chloride and the no charge oxygen gas. And similarly, down here we have a compound of hydrogen and oxygen here, and the two elements are over here on the right. So it's an oxidation-reduction reaction. In Texas City, Texas, on April 16, 1947, there was a great disaster. The French ship SS Grand Camp was berthed at 9:12 a.m. It was carrying a cargo of fertilizer, ammonium nitrate, that had been used in World War II as explosives. The ammonium nitrate caught fire. The entire cargo and ship exploded, even while firefighters were trying to put the blaze out. And here's a quote: "The entire dock area was destroyed, along with the nearby Monsanto Chemical Company, other smaller companies, grain warehouses, numerous oil and chemical storage tanks. Smaller explosions and fires were ignited by flying debris, not only along the industrial area, but throughout the city." And another ship nearby, even though it had been towed away, also exploded. It was carrying ammonium nitrate. Clearly, this was not a simple decomposition. To release so much energy, a reaction must be an oxidation reduction. The ions involved, ammonium and nitrate, are responsible. Ammonium nitrate is composed of two ions. It is an ionic compound. Look at the oxidation numbers. In the ammonium ions, the nitrogen is more electronegative than the hydrogen. Therefore, we assign it all the electrons. And what is the oxidation number on the nitrogen? Well, you may have done it before, but you can easily show that it is -3. In nitrate, the oxygen is more electronegative. Oxidation number of this nitrogen in nitrate is +5. The oxidation numbers are different in the two ions. Here's the ultimate physical toll to people: many injuries and 581 deaths. The reaction. Well, we're not quite sure what was going on in the hold of that ship, but we know that nitrate is a powerful oxidizing agent, and ammonium ions are a powerful reducing agent. One of the reactions proposed is ammonium nitrate decomposing to dinitrogen monoxide and water. That's an exothermic. It gives off heat. The detonation, which we can see even in the laboratory with very small quantities, is probably even more energetic. The ammonium nitrate decomposing into elemental nitrogen and oxygen and water. That's why we know that explosive compounds are very high energy. And that's why we must take special care not to heat anything explosive, because it just takes a little activation energy to make them detonate. Nitroglycerin, trinitrotoluene, there are just literally hundreds of explosive compounds, and they don't simply decompose. They decompose by oxidation reduction, giving off a whole lot of energy, a lot of hot gas, and they can be extremely dangerous. These are not simple decompositions. So when you're tempted to say it's a decomposition, make sure it's a simple one by always looking at the oxidation numbers and seeing if they change. If the oxidation number changes from reactant to product, then you do not have a simple decomposition, you have a oxidation-reduction reaction.